Problem 18 is another disk washer and shell method problem. So it says, which integral below determines the volume of the solid obtained by rotating the region bounded by these two functions around the line x equals -1. So at first glance, it looks like every single one of them is a disk method problem, so it looks like it's always r outer squared minus r inner squared. So I'm not going to bother with shell method in this case. I'm just going to try to set it up with disk method. So when I look at disk method, I draw my little line here, and the first thing I notice is that because my sliver of area has to be perpendicular to this axis, I need a dy. So what that means is I need to get all of my functions in terms of y to be able to integrate this. So I do know that volume is equal to pi integral r outer squared minus r inner squared. And now I know that I need to at least have dy. So to figure out what these are going to be in terms of y, let's take a look. So if I try to get x by itself here, I have y over 2 quantity squared plus 1 is equal to x. So that's my first function. And my other function is pretty easy. So that's just x equals, and then I have y plus 1. Okay. So now I have them all in terms of the variables I need. So now I can start to determine which one is my outer and which one is my inner. So if I'm looking from here to here, my outer is going to be this line, so it'll be this function that I have now transformed. And the inner one will be the curved shape, the parabola. So now that I know that, I can go ahead and try to set up this integral. So v is equal to pi. And of course, I'll figure out the integral bounds last. If I look at my r outer in this case, my r outer is going to be, let's see, so I have y plus 1, and I need to take into account the fact that this is offset. So the fact that this is offset means that I'm going to have to subtract off -1. So it's going to be this radius to here minus the distance to the radius there. And the reason there's no term when it's centered at the on the y-axis is because if you subtract off 0, you still have 0. So the only time we need to take this into account is when our axis of rotation is offset. So this is r outer squared minus y squared, y over 2 quantity squared plus 1. And now I have minus -1, and that's all quantity squared. Cool, okay, and then I have a dy out front. So if I go through and just do a little bit of algebra, I end up with y plus 2 quantity squared minus y over 2 squared plus 2. And then this is quantity squared as well. There's a dy. Now the last thing I need to do is I need to figure out my boundaries. And remember, they do need to be in terms of y. So I can't plug in these together because these will give me the values of x at which they coincide. I want the values of y. So I need to set this equal to each other and solve from there. So in this case, I end up getting y squared over 4 plus 1 is equal to y plus 1. So my 1's cancel, and I'm left with y squared equals 4y. So I can go ahead and I can factor that. So if I pull the 4y to the other side, I end up with y squared minus 4y is equal to 0. Factor out a y. Y minus 4 is equal to 0. So I have y times y minus 4 is equal to 0. Solve for those boundaries. I set them both equal to 0. Y equals 0. Y equals 4. So that tells me that my boundaries in this case should be from 0 to 4. So you have to be careful because, again, if I set these equal, I probably would have gotten, I think it's 1 in 5 is what the x value. And I believe that actually is an option for one of my integrals. Actually, it's not. Because we already knew what the inside was supposed to be. So 1 to 5 would have been incorrect in this case. So 0 to 4 are the correct boundaries that we want. So now, our final answer is D.
The Teaching Center, UF's Learning Resource Center.